Can you put the full screen, please? Can you put that? Great, thanks. Okay, so my thanks to the organizers for the opportunity to speak here. So I will speak about some work that I've been doing for quite some time on quantization of real semi-simple Lie groups and associated homogeneous spaces. So I should say that some of this work is also jointly with my student Dzokou Talla. So I'm of the same cult as Bob, so I also like my Lie groups. So you've seen this list already this morning. In my talk, I will be mostly working with compact, simply connected compact Lie groups. I see that I forgot my compact there, but so U is always connected, simply connected compact Lie group. The simply connected is not that essential, but it just makes some statements less awkward. Okay, so when things are simply connected, they are even nicer than in general. Okay, so we have a very nice series of compact Lie groups that we understand very well, as well as their representation theory. And we actually want to use them as building blocks to go beyond to more complex objects. And the way we do this is via a very well-known process in mathematics. Is instead of looking at the object itself, we look at some associated objects, and then this associated object turns out to allow much wider generality than the original object that we started with. So in this case, we start with sets with structure, but then we look at their associated functional algebras. So in the case of a compact Lie group, what we will do is we will basically look at the very restricted algebra of functions on this compact group, namely those which are generated by matrix coefficients of finite dimensional representations. So this will give us a very nice algebra of concrete complex valued functions on our original compact Lie group U, but it endows U with some extra structure. It actually makes U into something which belongs in the realm of algebraic geometry, and more precisely real algebraic geometry. So first of all, it's going to be a finitely generated algebra. And what makes it real is that it's stable under complex conjugation. So if we look at all these matrix coefficients, it's easy to see that they will actually be stable under complex conjugation of a function. And moreover, we can find back our original set U just by looking at characters of this algebra, which behave well with respect to this star structure, with respect to complex conjugation of functions. So if we have any algebraic algebra map from functions on U to the complex numbers, sending the star to just complex conjugate of a complex number, then actually all these characters need to be of the form evaluating some element of U, and this is one-to-one correspondence. Okay, so this puts U into the framework of affine real varieties, and then we have some coproduct around which allows it to be viewed as an affine real group. So this is kind of like a starting point for a series of operations we can do. So we already heard this morning about associated complex Lie groups. So this is an operation which is very easy to establish via this procedure. Instead of looking at the characters which preserve the star structure, we just look at all the characters. So now we forget that there was actually a star structure around. And then it turns out that this is really a larger set, and it can be identified with some complexification of U. Okay, so now we are in the realm that algebraic geometers really like, namely complex algebraic geometry. So G, this set of characters now obtains the structure of an affine complex group, albeit in an abstractly presented sense, as a space of characters. But the point is that somehow, from the function algebra point of view, there's very little difference between the functions that we get on the character space here and the original concrete functions we had on our set U. Because we have a natural inclusion of U inside G. U is simply those characters which preserve the star structure. And it turns out that the restriction functor from this one to this one is actually going to give me an isomorphism between the algebras. So really all I did is I took my algebra here with the star structure, and I forget the star structure, and then it turns out as a complex algebra, I view it as functions on this complex, on this affine complex group. So this G is an abstract, so this is an abstract way to obtain the complexification of my original U as a affine complex group, but then it's somehow by miracle, as Bob already said, it gets all the extra structure that you want from it. So it actually becomes also a topological group for a nice Hausdorff topology. So we can see it as a locally compact group just by endowing it with pointwise convergence topology. And not only that, together with this locally compact group structure actually comes a unique structure as a Lie group and as a complex Lie group. Okay, so the same object can be viewed from many different aspects: algebraic geometry, topological groups, and then differential geometry. Okay, and each of these will have their own characteristics and their own structures that you would like to somehow take beyond into the quantum realm. And in this talk, we will mainly focus on the first two, and we won't say anything about complex structures. Okay, so one thing that is very important to note is that this isomorphism here between the function algebra on G and the function algebra on U, it actually allows us to transport structure. Because as an algebra, these are really the same objects, but we know that this one comes equipped with some extra structure, namely a star operation. So what happens if we put the star operation from one side to the other? So since the restriction map of functions on G to functions on U is an isomorphism, I can take this star, take it to the other side, and then see what actually does this star operation do if I view my function as a function on G, on the bigger set G. And this is actually a really important structure in the setting of Lie groups, of complex semi-simple Lie groups, because this is what is going to give you the well-known Cartan involution. Okay, so this theta, if I view G as a set, this is just some group isomorphism, which is involutive from G to itself. And I write it in the following form. So I view it as G being sent to the inverse of some operation star applied to G. Okay, and then my star structure, it's written in this form. So it's applying theta, applying my function, and then complex conjugate. Okay, so this theta is completely determined by this star structure, which a priori was something very normal, namely just taking complex conjugates of functions, but it gives me a very interesting structure on G. And the reason why I write this as G star inverse is because it's something you know very well. If you represent your group as a matrix group, just as matrices on some vector space, then it really, if you present things well, becomes complex conjugate transpose that you know for matrices. So if you look at just the example of SUN, then up to some isomorphism of sets, you can really identify the complexification with SLNC. And indeed, Cartan involution becomes just taking conjugate transpose and then the inverse. Okay, so in some abstract way, you get back some structures which are somehow very easy or very natural from the viewpoint of matrix groups. Now, this already hints somehow a little bit vaguely at the importance of involutions in the theory of Lie groups, because this Cartan isomorphism of G with itself, it's an involution. If we apply it twice, we get the same map. We get the identity, sorry. So now we can look at more general involutions. So if we start with our compact Lie group U, we are actually going to consider general involutions on this compact guy. Okay, so kappa is just a Lie group, a map of Lie groups from U to itself, such that kappa squared is equal to the identity map. And the reason and the fact that we start with this involution on the level of the compact Lie group means that it lifts, first of all, to the complex Lie group, associated complex Lie group. And this is just because of the way we constructed G as this character space. But then also, because of this construction, it automatically commutes with Cartan involution. So not only do we have, from the start, one involution, but we actually create a new involution simply by taking this composition here. Because I have two involutions which commute with each other, so their composition is again an involution. Okay? And it turns out that somehow this easy setup of just a pair of involutions really creates a very rich structure in the setting of Lie groups. So it's basically the basis of how to construct non-compact semi-simple Lie groups, starting from compact Lie groups. And so this is basically Cartan duality in a way. I write here Cartan square, but I present it more like a diamond. So really, we started with this U. We had some extra piece of data, namely this involution kappa. And so kappa was an involution of Lie group, so it means the fixed point, which I denote as K of kappa. Okay, this will be a compact Lie subgroup of U. On the other hand, U itself, we can view it as fixed points of G under theta, because theta we think of as complex conjugate transpose inverse. So the fixed points of that operation are exactly the unitary operators.
K kappa and K comma kappa. What's the distinction?
K kappa and K
superscripts of kappa theta. Kappa theta.
Yes. So basically here I'm looking at all the points in G which are fixed by both kappa and theta. Yeah. Yeah. Exactly. So that's really the fixed points of kappa of the fixed points of theta. Okay. But since I told you the composition is also an involution, I can look at G and now take the fixed points for the involution kappa composed with theta. And this will be a group that I will denote L kappa. And this will be in general a non-compact, a real semi-simple Lie group. Okay. So this is a very nice procedure that allows you to go from compact stuff, namely an inclusion of a specific type of compact Lie groups, to something non-compact, namely a real semi-simple Lie group L kappa. Okay. And up to taking finite covers and finite index stuff, this really gives you all real semi-simple Lie groups by this construction. So we kind of want to take this as the basis to go to the quantum setting and consider quantizations of these objects. But let me first just illustrate, well, first actually there's some extra structure that I want to put in the background. So as you already saw in Bob's talk this morning, what's really important when you quantize is that you actually take a fixed presentation of your associated Lie algebra. And what this information amounts to is that inside our compact Lie group U, first of all, we fix a torus, okay, so a maximal torus T. Now, when we complexify, this torus will become a complex torus inside the complexification G of U. And then on top of that, we will choose some Borel subgroup. So some specific solvable group, which is in between H and G. Okay. So you think of SLN, you think of H as diagonals, you think of V as, for example, upper triangulars. And this, once we choose H, the position of B, it's kind of discretized. There are only a finite number of positions that it can be in. But since we have this structure, this torus and Borel, which are important for quantization, kind of like a direction for quantization, if we want to quantize also our involution kappa that we chose, we better make sure that it's in a nice position with respect to this extra data. And the problem is that this can be done in many ways. There's many positions that you can put your compatibility of your torus and Borel and the involution. And so it's kind of like I present it here as a dial. So you can basically think of it as conjugating your structure. So for example, we can conjugate by some unitary this set of inclusions. And then we can see, okay, with respect to that precise position on the dial, what does my kappa do? And for certain positions of my inclusions that I choose here, I will get something nice, namely my kappa will preserve my torus. Okay, and then what will happen is that automatically it will take my Borel to some other Borel. Yeah? Maybe not the same one, but always a Borel, something that is normalized by the torus. Now, what is nicest is, of course, if it would actually preserve the torus. And this is possible. So it's always possible to find some conjugation. I put it here as the maximal one, which will actually take your original Borel to itself. And because of the way that this position is described by diagrams, I call this the Vogel position. Okay, it has some other names which are more technical, but I like to present this as the Vogel position. So this is the one which really preserves all the structure, nu sends H to H and B to B. And then on the other extreme, we have the position where the involution kappa will actually take B as far as possible from itself. So it will try to put it as much as possible into the opposite Borel. So think of going from upper triangular to lower triangular matrices. And it will not always be possible to put it really completely into the lower Borel, but there is one involution or one position where you really get a maximal amount inside the opposite Borel. Now, since our Cartan involution theta actually takes the Borel to the opposite Borel, this is the same thing as saying we're looking at the position such that the composition of my involution kappa together with the Cartan involution will take B as much as possible into itself. And so it's kind of as nice as possible with respect to the composition of our involution and to the Cartan involution. Okay? And so this will be called, this I will call the Satake position because it's described by Satake diagrams. And this one is nice because it allows you, in this position, a good decomposition of your associated real semi-simple Lie group L sigma into its compact part and its solvable part. Yeah? So think again of SL and R. We take SON, the orthogonal rotations, and then upper triangular real matrices. Yeah? So we have these two extreme positions that we can put our involution or our Borel in, and they both behave very differently when we quantize them. And basically, a little bit of the goal of my talk will be to describe to you how these two extreme positions look like when you try to quantize them. So just an example that I had already promised in rank 1, just because this is very visual. So here, our compact Lie group, as we already saw this morning, is U2. Torus diagonal matrices in SU2, described by one-dimensional torus. Its complexification inside the Borel of upper triangular matrices, inside the complexification of U, which is SL2C. Okay? And so in this setting, because there's only rank 1, we only have two extreme positions. So if we take our conjugation here, our involution to be the conjugation with this matrix. Okay? And if we choose it diagonal, well, it means, okay, it's a diagonal, it's actually in a part of the torus here. So it will preserve B. Okay, so this is a Vogel position. And if you look at associated fixed points of Cartan involution composed with nu, you find the group SU11. On the other hand, if I rotate things a bit and I conjugate this matrix to the flip matrix with the appropriate sign, then I can do the same position and now the same procedure, and now the fixed points of sigma composed with Cartan involution will give me SL2R inside SL2C. Okay. So it's the same group up to isomorphism, but they're in different positions with respect to SL2C. Okay. And this one is nice because it has an associated Iwasawa decomposition borrowed from the one from SL2C. Okay, so this is kind of like the classical setup that I wanted to describe to you. So now I move to the quantum setting. So we saw this morning quantization already appearing on the level of universal enveloping algebras. So we also have this associated quantization that we can do for function algebras. So because I'm interested in associated operator algebraic stuff, just like Bob this morning, I will actually restrict to Q larger than 0. And then it's the same game. You're basically trying to find a nice deformation of the original algebra of regular functions on SU2. So this one here you can describe as an algebra generated by 4 generators, just satisfying the determinant relation and with an appropriate star structure mimicking the precise compact form that you are using here. And then when you quantize, you are introducing in some way appropriate Q factors which allow you to preserve all the extra structure that you want, such as the Hopf algebra structure and the Hofstadter algebra structure. And so this is a very precise process. You can't just throw in parameters as you like. It's a very precise process, but it can be done. And then you get commutation relations like alpha beta must be q times beta alpha. The determinant relation gets q deformed in this way. And you get actually also some q factors when you consider the star structure. Okay, and there are some extra relations. I won't put them all there. And also the coproduct, it actually nicely deforms, and the coproduct is really the same as it's on the classical setting. Okay, so that one is actually really nice. And I didn't really tell you this in the previous part about the associated Lie algebras, but again, I'm happy that Bob already mentioned some stuff about Lie algebras this morning. So these function algebras, you can dualize them. You can put them in duality with universal enveloping algebras. Think of applying some differential operator and evaluating at the unit. That's how you get the duality between universal enveloping algebra and function algebra. And they're also generated. They also have a nice presentation by generators and relations, which we already saw this morning. So here I actually don't need to repeat what these commutation relations are. There's also coproduct around on this dual side, but I won't really emphasize it in the talk. So here I present it just in the rank 1. In general, it's also part of a well-known story where Drinfeld and Jimbo were the first ones to consider the story from the point of the universal enveloping algebras. Voronovitz kind of independently started from the function algebra side, and then work of Lewandowski, Soibelman were the first to bring them together in arbitrary rank to show that they really talked to each other and were part of the same story. Okay, so now that we know, in some sense, that we can deform our compact Lie groups, I now want to go to the setting of their associated complexification. And here already I have to somehow make a choice. Do I want to quantize things as in the setting of complex algebraic geometry? Well, then I know I don't really have to do anything because my function algebra for the complex affine group G was really the original function algebra on U. I just forget stuff. I forget the star structure. Okay, so if I have G as an affine complex group, its function algebra is just the original function algebra on U. And also in a quantized setting, I just take OQ of my compact Lie group and I forget the star structure. This is OQG. But I could also consider G as a topological group or as a real Lie group. And then things become much more interesting because now I can kind of play with all kinds of extra structures. And if I want to view G as a real Lie group, or actually as a real algebraic group, I need to force conjugate functions into the game. So I can actually iterate my construction that I had. And now instead of saying, okay, I only look at complex analytic polynomial functions on G, I throw in their complex conjugates. So I throw in some extra copy of OG, but with the opposite complex multiplication. Okay, so basically O of GR is just those functions on G generated by analytic polynomials, holomorphic polynomials, and anti-holomorphic polynomials. And these are completely separate, so we really get like a tensor product of OG with OG complex conjugate. So again, this gives some kind of strategy for quantization. But there's also a different thing we can do. Because I also told you a little bit already about Iwasawa decompositions. So if we had our setup of where we chose a torus and a Borel inside G, then from the viewpoint of the associated real structure, I can decompose my H, my complex torus, into its compact part T, and then its real part A. And also B itself becomes composition of TA, and then the nilpotent part of B. Okay? So again, think of unimodular matrices, real positive diagonal matrices, and here the strictly upper triangular matrices in SLN C. Okay? And then Iwasawa decomposition of G is just saying that G is actually as a manifold, the direct product of the compact part U and the non-compact part A times N. Okay. So there's also a way to then say, okay, maybe the natural functions to view on G is just taking the tensor product of the ones on U, tensor the functions on the part AN, okay? And this is also a valid point that you can make. This is also a valid construction. The only thing that is a bit subtle is that, so these would now be star algebras, okay? So U we know already, and A and R, it's also some kind of, you can view it as some real matrix group. So it would also have some star algebra of regular functions on it, except if we really want to get this A here, this is what happened already in Bob's talk this morning also, we kind of need to view it as a spectral star algebra. So it means if we want to find back the set A and R from the function star algebra, we actually can't look at all the star characters. We need to look at those ones for which the A part gets sent to positive numbers, and just like we saw in Bob's talk. Okay, but up to this technicality of that, we have to take some special positivity constructions. We can really view this tensor product as some algebra of functions on G. Okay? And both this one and the one that I had before here, I guess this should really be GR. I apologize. This really should be seen as two different presentations of functions on GR. Yeah? And so we can use both of them as a kind of basis for quantizing G as a real algebraic group. So for the first one, as I said, we don't really do anything. We take OQG and OQG as a formal copy with complex conjugate structure. But when we quantize, we actually need to introduce some non-trivial commutation relations between these two. Okay, and I'll tell you a little bit about them in a moment. On the other hand, if we take the second quantization, as a function algebra, we don't need to do anything. We really just take quantization of this one. But then for the second one, I do something strange. I put here UQU. I put the quantized universal enveloping algebra. And the reason is that it turns out by some very deep formalism due to Drinfeld, that function algebra on this one can actually quantize into quantized enveloping algebra of this Lie algebra U. So this was really developed by Drinfeld, but then Gavarini kind of put this on a much more formal and rigid basis. But it basically tells us of a certain duality between quantized universal enveloping algebras and quantized function algebras. Okay, and then there's also some way by means of R matrix formalism. So I won't go into detail about this. So these commutation relations that we have here, they are governed by some very strong algebraic structure going by the name of R matrix formalism. It allows us to go from this, it allows us to introduce, first of all, a twisted commutation relation between our two components, OQG and complex conjugate of OQG in this picture, and to create a map to our other picture where we just had the tensor product of algebras of OQU and UQU. Now, the thing is that since we want to actually view this as Hopf algebras and not just as algebras, we want to also encode the group structure, then things get turned around. So on this picture here, even though this algebra structure is kind of made more difficult by this twisted commutation, the co-multiplication is really just co-multiplication on this part and this part. Whereas on the other side, on this function algebra side, you can't really implement the co-product in a very nice algebraic way. So it behaves a little bit badly. And you have to view things from the dual side to really get it to work algebraically. But these are some technical details. In a way, the short message from this is that the first quantization is somehow the one which behaves nicest from the viewpoint of algebra. The second one is the one which behaves nicest from the viewpoint of representation theory and analysis. And I put here the names of Majid and Hodge and Kramer because they kind of, so Uli, he worked out this duality between this picture here and the dual of this picture here in a paper of this. Okay. Right, so we kind of have these two pictures and they will be related to the two kinds of quantizations that I want to perform. for my real semi-simple Lie groups. So as a spoiler already, this first quantization will be the one that behaves well with respect to the Vogel picture, whereas the second quantization will be the one that behaves well with respect to the Satake picture. Okay, so this is what I want to explain in the next few slides. So I will start with Satake picture. So this is the one for which the Iwasawa decomposition just gets transferred from the overarching complex Lie group to its real semi-simple Lie subgroup L. So it means that if I am in Satake position, I have my real semi-simple Lie group L sigma inside G, and the Iwasawa decomposition for G just gets restricted to an Iwasawa decomposition for L. Okay, so this is just a presentation for L sigma. And now I will try to do the same thing as I had on the previous slide, where I will try to quantize the different parts. I will try to quantize K, and I will try to quantize A0, N0. So I remind, okay, this was the picture where I had separated somehow the OQU and the OQAN, where we said, okay, OQAN is actually the same thing as a star algebra as UQU. And if we take duals, well, I know OQU gets transformed into UQU, and UQU gets transferred into OQU. And as I said here, it's just a tensor product of algebras, but with a twisted coproduct. So if I look at the dual, now I really get an non-trivial commutation relation between this algebra here and this algebra here. But the coproduct is now just a coproduct here and a coproduct here. And this twisted tensor product is something that you can do whenever you have two Hopf algebras in pairing. And so it's something completely general and not related to anything deep like the Drinfeld duality. And this is just a more direct construction that you can do when you have a pairing between Hopf algebras, Hopf star algebras even. Yeah? And this, what is called Drinfeld double, this will then give you something which is dual to the function algebra on GR, namely quantized enveloping algebra of G, complexification of U, but viewed as a real D algebra. Okay. So we have something now quantizing G as a real D algebra. We have our L inside respecting the Iwasawa decomposition. So somehow we expect that if we want to quantize the universal enveloping algebra of the Lie algebra of L sigma, it will somehow live with a factor in this part, and it will live with a factor in this part. And this can indeed be done. And the important ingredient has a long history, and many people considered different cases, but it was Letzter who really kind of made the defining overarching definition of how to quantize, well, let's say the enveloping algebra of fixed points of a compact Lie algebra of a compact Lie group involution. And so remember, our K was fixed points of U under this Lie group involution sigma, and she found a way by generators inside UQU to produce a good copy of something that should be viewed as a quantization of the universal enveloping algebra of K. And then just by duality, it's somehow clear what should be on the other side. So on the other side, we take the only thing that we can kind of immediately construct starting from the function algebra and a subgroup, namely the function algebra on an associated quotient space. Okay, so U mod K. Now, one tricky thing in this business is that these things are not Hopf subalgebras. They are only co-ideal subalgebras. So they're one-sided co-ideal subalgebras, meaning that if I apply coproduct to this thing, it will only land up with one of its legs inside the algebra, and the other one will go outside. Now, for the second part, this is somehow obvious because here we're not working with a group. K is not necessarily normal in U, so U mod K does not have a group structure. So we only have U acting on one side, namely by right multiplication, and that's all we can do. So for this one, it's somehow natural that there's a one-sided operation, but it's somehow mysterious that also for its dual, it's a one-sided operation when we quantize. And now somehow you can kind of see what happens. In the previous picture, I could view I could view UQU as function algebra on AN. In the dual, I view function algebra, quantized function algebra on U as a quantization of the universal enveloping algebra of A plus N. And then it turns out, again, by some generalization of this Drinfeld duality principle that was also investigated in more detail in papers by Cavarini and Ciccoli, that this quantized function algebra on the coset space can really be viewed as a quantized universal enveloping algebra of the AN parts of L. So basically, let's deconstruct this inclusion here. This duality here was known by Drinfeld and Ciccoli-Cavarini, but somehow the idea of putting these two together inside the quantized universal enveloping algebra of GR, this I had not seen before. So it's a very easy construction, knowing everything that has been done already, but I have not seen explicitly that people have considered this kind of twisted tensor product of a co-ideal and its dual. And this is what we propose as the quantization of the Lie algebra of L sigma. Okay, so it's really composed of some twisted tensor product of UQ of the compact fixed points and the part A0 plus N0. So the point is that in the end, we constructed the one-sided co-ideal UQ L sigma inside UQ GR. So this is the first kind of quantization that we do. And one thing that might be a bit disappointing at this point is that we only constructed a co-ideal. Okay, because when we want to do quantum groups, we want to look at representations and we want to take tensor products of representations. But if we only have a co-product which preserves one leg and not the other, well, we can't take a tensor product of two UQK representations because we can't magically extend the UQK representation to a UQU representation. There's no canonical way to do that. So you seem to be stuck. But it turns out that there's a solution, and it turns out that there is actually a way to multiply representations. So first, I won't say anything, I won't really say a lot about how this looks in the analytic picture, but the point is that because of the setup and because of what was already done in the analytic setting, it really is completely very straightforward in this approach to go from this quantized enveloping algebra to some associated universal enveloping C-star algebra. The point is that both parts are really well behaved. UQK is a subalgebra of UQU, and UQU only has finite dimensional irreducible representations. So it's easy to restrict to UQK, and you know immediately which kind of representations you're interested in. And OQ of U mod K, this is also some star algebra, which is automatically well behaved in the sense that any of its representations on Hilbert spaces will automatically be bounded. So again, from the analytic point of view, it's really well behaved. And then we look just at Hilbert spaces having a representation decomposing into irreducibles, finite dimensional irreducibles of this one, with some representation of this one and the appropriate commutation relations. Okay, so this is quite easy to construct universal. Yeah. So what I do, so I have UQU, I have my type 1 representations. And for UQK, I only look at those ones appearing as sub-representations of UQU representations. Okay. And for my other one, well, it's a compact homogeneous space, compact quantum homogeneous space. So automatically all its star representations are bounded. So I just look at Hilbert spaces having a star representation of this one. It's automatically bounded. And a star representation of this one in the sense that it decomposes into, with possible multiplicity, irreducibles of this one, which are finite dimensional. So there's no analytic obstructions. Yes, but the point is, because I only look at those representations which restrict from ones from UQU, that they actually will have the right spectral conditions already. So it's not like I'm looking at all the possible admissible representations of my universal enveloping algebra. I'm already restricting by putting these spectral restrictions using this inclusion. Sorry? Irreducible irreducible in the sense that Admissible in, yes, yeah. I'll come back about the admissibility later, but there's no problem to define a reducibility. You have a dictionary between the algebraic and the analytic. So, okay, so there's no problem to make this analytic, to look at star representations on Hilbert spaces. As I told you, it's a co-ideal, so there's no a priori way to multiply representations of this C-star algebra. But it turns out, it turns out that actually there is some hidden way. So even though it's only a co-ideal, the representation category of the C-star algebra turns out to be monodal, turns out to have a nice tensor product structure. And for this, I won't go into detail at all. Joel will say something more about this in his talk. But it turns out that the representation category of this C-star algebra is isomorphic to some other category of what we can say are equivariant bimodules. So I won't explain notation here very much, but it basically means this LQK is some analytic version of UQK. We look at bimodules over UQK, which also have a comodule structure for UQU. Okay, and then they have to be compatible. And because now we look at bimodules, we can actually take balanced tensor products and we have a monodal structure. And it turns out, because of the analytic framework, that this really gives us an isomorphism between these two categories, so we can just transport the monodal structure from this one to this one. So it's a very roundabout way to construct the monodal structure, but somehow it's a very natural one or a very canonical one. Okay, so let me see. So I just wanted to present the picture. So in the rank 1, everything becomes very amenable to direct computations. Here, our subgroup that we want is, I didn't write it, but it's UQSO2. In the Satake picture, inside SU2, our compacts, our fixed points of the involution is SO2, and it's just the algebra generated by E minus E star. In the dual, for the quantum homogeneous space, it also has some nice presentation by generators and relations. Everything is purely algebraic. We just try to find enough representations for these generators satisfying the commutation relations, and we can completely classify these irreducibles, and they turn out to be some kind of quantum version of what is known classically. We have some even series, some odd series, some discrete parts, and some continuous part. Okay. So I just present this as a picture for illustration, so I won't go deeper into this. But it gives us kind of what we expect, something that whose representation theory still looks very much like the classical set, like the classical one, but that is somehow deformed a bit. Okay, so let me in the remaining minutes try to tell you a little bit about what we can do then for the Vogel picture. So here we had an involution of U, we extended to G, and now it's in such a way that it actually preserves all the extra structure. So it sends B to B and it sends H to H. So in this setting, it's very easy to actually construct an involution of the quantized universal enveloping algebra of G just by composing the star structure or the thing we have already from the Cartan involution with the involution nu. And it means that we get UQL nu, which is just the algebra UQG, but with a new star structure. Okay, so it's really saying instead of looking at usual compact form, I look at some other form, which is no longer compact. So it's UQG with this star operation that I view as UQ of the Lie algebra L nu. The problem, however, is that even though this is a super easy algebraic construction, it does in no way lead you to some analytic counterpart. So this has been tried many times in the past, and many people have stumbled against this and tried to find very difficult solutions to get out of this. But the end point seems to be that there is really no easy or canonical way to go from this algebra to some associated C-star algebra. Okay. There's just some analytic obstructions which can't be resolved. But it turns out that if we look at the dual picture of homogeneous spaces, that there are some more things to say. So I presented you this OQGR, which was OQG with an extra complex conjugate copy and some commutation relations. This UQ of L nu, this UQG with the new star structure, it does have some natural action on OQGR. Okay, I'm lying a little bit because I actually need to change the commutation relation slightly to get this action, but it doesn't really matter too much for this talk. So I can look at the associated fixed points of UQL nu, and basically you should think of this as infinite functions on GR, which are infinitesimally invariant under L nu. Okay, and somehow you would want to say, okay, if it's a function that's infinitesimally invariant under left translation by L nu, then really it's kind of like a function. It must be a function that's also invariant under the Lie group L nu. And just no, yeah. But the problem is that algebra is not always cooperative. So if we only do this construction on the algebra level, we somehow get too much. We get too many representations in a way. So we get something that is known as a categorical quotient. And then we want to find, okay, so this is some star algebra. And then we want to say, okay, these are the star representations that are actually interesting to study. And that will give us some quantization of the proper coset space G mod L nu. Okay. So these spectral conditions, I will explain a little bit the setup in the next slide with an example, but they're somehow not that easily accessible. And they're not as easy as in the case of UQU, where we just say K needs to go to positive operators. Here we need to do a little bit more work to say exactly what the positivity conditions are, but they can be formulated. And in that way, you can somehow make some quantization of the C-star algebra of functions on G mod L nu. So what I mean in this example is that if I look at SLM plus NC, and I look at SUMN inside, then the coset space I can kind of see as the orbit of the matrix of M units in the upper hand corner left and minus units in the lower right corner. And then I take the conjugation action of SLM plus NC by this conjugates action. So it's not so hard to see that this is really a presentation of this coset space. But then I somehow want to present this in an independent way, not as an orbit. So what you can check is that these are actually all the matrices which are Hermitian, have this determinant, and then you need to look at some signature of this matrix. Okay, and this signature is exactly what you want as spectral conditions. So there's some way to frame this also in a quantum setting. I won't go into this, but this is where the spectral conditions arise. Whereas if I would just look at the categorical quotient and I look at all the star characters of this algebra of fixed points, then I would actually find all Hermitian matrices with this determinant where the signature condition has disappeared. Okay, so I somehow have to do some extra work to locate the proper coset space into this categorical quotient, but it can be done. So maybe for the last 2 minutes, I wanted to present some open questions. So we had now these two quantizations. One of the Satake position as actually some co-ideal, but with a monodal category of representations. And then for the Vogel picture, we didn't quantize the group, but we quantized the associated quotient space, the coset space. So some extra questions which are intriguing to me is, for example, we saw that these are just extremal positions. So what can be done if we choose our position of our Borel and torus and our involution kappa in such a way that we're not in the extremal position? Okay, is there somehow a quantization also of something that is intermediate but still preserves the torus? And somehow I think that would be important to understand the representation theory of one of the quantized Lie group in Satake position, because that is what you see is relevant also when you want to study representation theory of semisimple Lie groups. These extra carton subalgebras, they're somehow very important. Okay, and in this framework, I wanted to say that if you do this on the level, if you want to understand the representation theory of just the associated complex Lie group as a real Lie group, okay, this was done, I would say, relatively recently by the work of Arano. Okay, so somehow for the complexification, and I guess Bob will tell something about this in his talks later, but for the compact one, it was already well known. For the complexification, it's kind of well known. And for the real one, it's kind of open to have some good understanding. For the Vogel and the Satake, there's a way to somehow compare them, because for the Satake, we had a quantum, co-ideal subalgebra, but there's a general formalism which allows you to take duals of co-ideals. So if I have this co-ideal inclusion, it also leads to a dual co-ideal inclusion. So I have some nice quantization of the coset space with the Satake involution, and I have presented to you how to construct it for the Vogel. Can we actually identify these two beasts? So are these actually the same C-star algebra with the same action by G, by quantum G? So the candidate for this is via some formalism known as K-matrix, which is some kind of companion theory to R matrix theory, but which seems to be a bit harder because it doesn't have all the structural properties you want. But some work in this direction was already done by Kolb and Stockman, and also by myself and Marco Matassa. Another open question is, this C-star algebra of this L sigma, is it type 1? So this would relate back to the admissibility condition that Bob was asking about. If we take an irreducible star representation of this guy here, does it actually decompose into irreducibles of the quantized enveloping algebra, quantized universal enveloping algebra of K, where the multiplicity of each one is finite? Yeah, so basically the irreducibles arise as finite dimensional subalgebras with finite multiplicity. And again, for the associated problem for the complex Lie group G, this was done by Arano in 2018. And then the last question is, can we also do some quantization of the Plancherel decomposition? So in work with Joel, we showed that these quantizations also always have some associated nice weight, which happens to be tracial, which is kind of surprising. And because of the type 1 condition that we had somehow supposed here, it means we should get some nice decomposition of this von Neumann algebra, C-star algebra, into irreducible components via some direct integral condition. Can we then explicitly identify the weight that goes with this decomposition? And here I can reference to Voigt Juncken, who achieved this some years ago, but I guess it was only recently published for the case of the and for the bigger complex Lie group. Okay, and so that's the end of my talk.
The time for one question, we are ready to present. Any question?
Maybe
Oh, sorry.
So why not? Yeah. So this thing on the
Yes, this is basically Takeuchi souped up to the analytic setting.
So then there is a co-marginal category of others that actually equivalent to the representation. I know, but it's already now it makes sense.
Yeah.
Yes. And this diagonal that you had somehow was attacking and instead of one and the other, you said that when it's right one, you just got two. So what is it dependent on the number of
well, you can count them, it's discrete, but yeah, you can probably look it up in some table in Wimberg or Chansky or yes, yeah. But actually, it's also not all of them that we're interested in some special ones, but.
I think we need to give further questions that the algebraic is different inside. So let's try to do the question.
I'm sorry.